This is an introduction to the 3F5lab. I'm not going to go into all the details because the handout is very thorough, but I'd like to just give an overview of how you're going to spend the next 2 hours. We're going to talk about caches, and to appreciate why they're so useful, I'm going to first go over why the inside of a computer is the way it is, memory-wise. So, we have a CPU, the number crunching part of the computer, and that's nowadays very fast. But we also need that CPU to work on data, numbers. And that data might well be contained, even nowadays, in a hard disk, actual physical piece of equipment that has to move. Of course, it might be something more small and flexible nowadays, but the same principles apply. Now, between the two, there's an area of RAM, rapid access memory, less big than the mass storage, and the CPU gets its information from here rather than directly from the hard disk. The RAM is slower than the CPU. It can't supply the CPU with data as fast as the CPU can cope with, which is a shame because we want the programs to run as quickly as possible. In fact, this journey to the hard disk can be thousands of times slower than the quickest possible journey that the data can take. Fortunately, when a computer runs, it tends to use the same variables time after time. It tends to use data which is close to other data. So it's not completely random, the access to the hard disk, and we can take advantage of that by putting here a small-ish bit of memory called cache. The idea is that when we go and get information from the hard disk, we store it in here in case we can rapidly use it again. And what we want to do is we want to maximize the journeys like that at the expense of these long journeys. So how do we do that? Well, we can use this space, cache space, in various ways. There's not an unlimited amount of it. We want to maximize the use of it. And what I'm going to do is to just show 2 quick and easy ways that we can use this cache. In real life, the caches are quite big. I'm a human, used to base 10, so I'm going to have a little cache here with only 10 slots in it to make life easy for me. So we're going to try to use this cache, and we're going to try to simulate running a very simple program. Let's suppose first I show you direct access mapping. So let's suppose we try to access memory location 71. Well, the cache begins empty, so the CPU has to go and look for what's in memory location 71. Rather than just use it directly, it stores a copy of what's in memory location 71 in the cache. But where? Well, in direct mapping, what we do is have a very simple rule so that knowing the location, we know the slot. And the rule I'm going to use is divide by 10 and get the remainder. So the value in memory location 71 will go there, and then the CPU uses it. Let's suppose then that we use memory location 13. Well, same principle applies. We do the division by 10, we look in this slot, is there a value there? No. Well, we store a value in there. So we're not actually exploiting the power of the cache just yet, but suppose now we look at memory location 71 again. The CPU will look here, the value will be there, and it will use it. So already it saves a huge journey, which is great. The cache has done its job. But suppose then we look at memory location 23. Well, the CPU will look in this slot in the cache. It will realise it's actually not the value it wants, because this value came from memory location 13. So it will get the value from memory location 23, and it will overwrite the old value and put it in there. So it's not a disaster. There's going to be contention for slots, and so on. Now that works pretty well in many circumstances, but there are situations where it can cause the system to run slower than it needs to. For instance, if we now go to memory location 13 again, the CPU will look here, the wrong value's there, it will have to go to the CPU, get the value, and overwrite here. But suppose then, for some reason, we went to 23 again. Things are getting inefficient. We're having to do loads of long journeys, even though the cache is nearly empty, because of this mechanism we're using. Is there an alternative way to work? Yes. So let's scrub out some of these values and look at a fully associative technique for using caches. We've still got the same amount of cache, but this time I'm going to use it in a different way. So let's take the same memory locations. Memory location 71, empty cache, so we've got to go and get the value that's there. Where do we put it? Well, this time we're going to put it in the first empty slot. 13, not in the cache, but there's a slot here, so we'll fill it in. Now we'll look at, for memory location 71, we have to look through the cache. We don't know where it'll be, so we'll have to search through all the cache. It's there, so we'll use it. This time, if we want memory location 23 and it's not in the cache, we don't have this contention. If there's an empty slot, we can put it in there. And so if we wanted 13 again, it hasn't been bombed by the 23 value. It's still there. So this seems to get over this problem of not exploiting the cache. This is going to use as much of the cache as is available. But this has a downside too, and that is that the CPU has to search the whole cache to make sure the value isn't there. So neither of those two approaches are ideal, but there is a sort of compromise arrangement, and the handout, the lab, will show you how to play with that. So the first part of the lab is where you're going to use a cache simulator. You can't, of course, fiddle around with the real hardware simulator, so we've given you one to play with, a bit of software. So the first part of the lab is going to play with that, gather some data. Then we're going to offer you two ways of doing sorting, and you're going to do a compare and contrast job on this, changing the characteristics of cache to see how that affects the speed of the two different ways of sorting. Then you're going to do the same thing again, this time for matrix multiplying. And then finally, having done this work with a simulator, you're going to do the same matrix multiplying, but with the real cache in the real machine, to see how the results compare with what the simulator suggests. So it's a fully contained program of events that you can try, and the idea is that at the end you'll have experience with caches, which turns up often in exams, so I hope this is going to be useful for future revision for you. You've got 15 days to write the report. You give in the report in the EIETL filing cabinet. It's an easy lab to do out of hours. If you have any problems, just contact me. Good luck.